Assalamualaikum dan salam sejahtera. So we continue our discussion about quantity steady flow. And for this question, so we have a tank like this. So you could see the difference. The tank is rectangular shape here. So and then it has one hole at the bottom here. So usually if you have hole like this, so they will give you a CD. So CD means the resistance of this hole. So I hope you could understand how to reflect the resistance or the or the losses of the hole like this. Okay. So the question is, please determine time to empty the tank. So we have, this is our basic idea. So we start with the continuity equation, which is the flow in must equal to the flow out. And then we compare the flow out is the what happened on the at the outlet here, and the inlet is actually what happened on the free surface at this area. That's why we take the cross-section area for inlet as this one, and we assume that the velocity, because we know that Q is equal AV, and the velocity here is actually the changes of height of this surface. That's why we change the V here into the terms of dH dt. Means the height different here over the time. Okay, so our basic concept is actually the continuity equation, because in this subject, in this course, we are focusing on water. So we are not using oil or another liquid, and we are not also use gas as our medium. So we are focusing on water. So so the basic idea is we must make sure that the continuity equation is conserved. So that's why we compare flow rate at inlet with the flow rate at outlet. Okay, so the difference is we assume that the velocity at inlet here is the changes of height of water level here after certain time. That's why we change the terms of velocity here with dH dt. Okay, so this is the flow in equal flow out, and then it is equal to AS, VS, AP, VP. So S here is actually the surface. So means surface at the inlet, and P here is the pipe. So whether it is hole or it is pipe, so we assume that in my notes, so I assume it is as a pipe. So and then here the area here you must reflect with the real condition of our situation here. So because our tank is rectangular, a square, so we write the A here is square. So please do not fit with idea pi d square over 2, because the area on that time is circular. So we use the equation for circle area. So we use pi d square over 4. But at this question, our area here is rectangular, so we calculate the value of the area. And we replace the velocity at surface or velocity at inlet with dH dt. And then we could substitute the value of cross-section area for pipe, means for hole for this question, is pi d square over 4, because the hole is in circular shape. So we substitute with the proper equation. So and then we replace the velocity of P here by using CD square root 2GH. So I think you could understand how to get CD square root 2GH, because I show it in my previous notes. And then you know what to do. So we rearrange this equation until we have dH dt on the left, and we have all the equation on the right, and then we solve all the numbers here until we get only one unknown here, square root h. So and then we could solve this one by integrating both sides, and we could get this term. We substitute the limits. So in this situation, because we assume this is a 0 and the water height is 2 meters, So and then we take 2 and 0 as its maximum and minimum limits. So we substitute with 2 and 0 here, so we get 650 seconds. Okay, so the problem about the limit is not critical. If you misplace, so mean if you put down 0 to 2, you will have the negative value. You will get negative 150 seconds. So the answer is still correct, but please declare your answer. For example, if you calculate, you misplace the limit here, so and then you will get 100 minus 650 seconds, and then please make a statement that okay, the time is 650 seconds. So please ignore the value of negative, but okay, but you must declare, you must make some statement that you take only 650 seconds as your final answer. Okay, that's case 3, and this is the case 4. So we have the rectangular tank, and it is connected with a pipe here. Okay, the question is still the same. So what is the time to empty the tank? Okay, in my tutorial, I will focus on time to empty the tank, but okay, I still have right to ask you how many volume the water has been flow out. Okay, please know about that, because the calculation to know how many volume, how much water has been flow out is actually depends on your understanding. Because in question number 2, when we have a cone shaped tank, okay, so I teach you, I show you how to calculate the volume of water after certain time, because you need to use a little bit your creativity to understanding from what so level to what level the water has been flow out. Okay, I think yang ini saya harap awak dapat pastikan awak boleh mengira isi padu air yang dialirkan keluar setelah beberapa saat. Okay. Kerana dalam tutorial saya fokus kepada masa sahaja, kerana dia akan reflect kepada apa nama tu, integration method. Okay, let's say we have this one. So we have the tank here, because the width is 2 meters. So we just assume it is something like this. Okay, so the length here is 2 meter. And then let's say the water is 2 meters, and the length here is 3 meter. So and then we have outlet at point 2 here, and the height is 2 meter here and 3 meters. So please be careful on this situation. You need to take limit as 5 meters and 2 meters. So this is the yeah.
Yang 2 meter belah kanan tu, kenapa gitu?
Okay, yang ini. Okay, so I will show you. So the 2 meters is, oh I'm sorry, bukan 3 meter. Okay, this is, okay, the height of tank is 3 meters. Okay, I'm sorry. And the 2 meters is the water level. So means that your limit must be 4 to 2. Okay, I'm sorry. Saya salah tadi Okay. Okay, so what I want to show here is, okay, please be careful, because sometimes the height of the tank might be different with the height of the water. So you need to take your limit for integration from the height of water, because you are calculating the velocity of water that comes out from the outlet here. So it will 100% depends on the height of the surface at inlet. Okay, saya minta maaf yang tadi. So and then in this question, I try to give you hint when you have F, you have diameter, you have length, and also you have K here. So the word K here, okay, so might be you are confusing with HF is equal KQ square that we learned in chapter 2 in Hardy-Cross method. Okay, so this is the simplification or the constant of the major loss actually. But in this situation, you know that we have F, D, and L, and this K will reflect the minor losses, the minor loss coefficient. Okay, I hope you could understand the situation of this question. Okay, So, and then first, okay, we should do the Bernoulli equation. So in this situation, you are not allowed to calculate just to simplify your calculation with V2 is equal square root 2GH, because this equation is actually valid if we have a whole like question number 3. Okay, because we don't have minor loss and major loss in a whole, but we have CD. That's why we just we could assume that we could have this one, but for this situation we have pipe. So and then from the note from the figure, we know that we have F, L, and D, and then we have K. So means we need to calculate the major and minor loss also. So we write our Bernoulli equation here. So this is the inlet, this is the outlet. So we know that the pressure at inlet is atmospheric pressure and also atmospheric pressure at the outlet. So we cancel the value, or we assume the pressure is equal to 0. And then velocity at the surface at the inlet is also can be assumed as 0. So we have 0 here, but the velocity at outlet is exists. Okay, please do not cancel the value of V here. Okay, because some student might be he confused with the idea of if you still remember my notes about pipe here, and I draw like this. So I put an A and B here. So I assume that the velocity is constant. So we cancel the value of velocity. Okay, please do not confuse with this diagram. Please do your Bernoulli equation based on the figure that you have in the question. Okay, so and then the value of Z here is equal to 0 because we know that this is the datum, so it's equal to 0 here. Now our Bernoulli equation will become like this. So this is the total losses, consists of major loss here and minor loss here. So we substitute all the value. Okay, please remember, for this solution, please do not substitute the value of Z1 here. If you substitute the value of Z1, so you could get the value of V2. Then you cannot do your integration process. Okay, so please let the value of Z1 here, that means the water level at inlet, as an unknown, or atau kita anggap dia sebagai satu pun boleh ubah, because now we need to build an equation to do the integration. So we substitute the value of Z1 with H here, and then this is the value of major loss and minor loss. So for sure we cannot calculate the value of V2 because we don't know what is the value of H. Then we could write the equation like this. So this is the value of K as shown in this question. So and then we simplified everything here. Okay, so we could write V2 is actually 1.445 square root H. So this is the equation to describe or to show the velocity changes of outlet. So and then what we do is we stick with the idea of continuity equation. Flow in is equal to flow out. So this is the equation. So we have AS, VS, AP, VP. Okay, in some textbook they will write as A1, V1, A2, V2. It's okay as long you understand what is your point 1 and what is your point 2. Okay, so because our tank is now a rectangular shape, so we take the area of area here is 2 times 3. So it's depend on the image, it depend on the question. So we replace the value of velocity here with dH dt, and then we substitute the area of outlet. So the area of outlet is a circular pipe. So we use pi d square over 4, and then we substitute the equation of Vp, velocity at outlet. So this is the value. So you know what we need to do is we will integrate. So we must bring the H term to the left hand side, and then we bring all the unnecessary items to the right hand side. So, and then we could get this equation and we integrate, and then we use limit 4 and 2 here, as I explained previously. So the water level must be taken from the datum, from the height of, from the outlet point. So these are 4 and 2. So if we calculate, we could get that T is equal 3870.66 seconds. Okay. Sampai sini ada masalah ke? Boleh ke?
Doktor,
Ya.
saya cuma nak tanya berkenaan dengan area untuk Q2 tadi kan? Q1 tu. Kita ambil 2 darab 3.
Sebab dia kata width 2.
Oh.
Maknanya lebar sini 2.
Betul.
Okey, boleh nampak
Saya salah salin tadi. Sorry, saya salah salin.
Okey. So video ni pun saya akan upload, nanti awak boleh check balik lah
Okey, baik dah.
okey. So awak snapshot ni senang elok. Jangan kalau tulis takut saya laju sangat pula. Awak print screen ni. Dekat komputer masing-masing nampak jelas ke nombor ni? 2. Nampak, okey. Okay, so maknanya sampai sekarang ni awak dah nampak idea dia mudah. First we develop the outlet velocity, the equation for the outlet velocity. Okay, rule of thumb, please do not substitute the initial height, because if you substitute the initial height, you will get the value of velocity outlet. Then if you get the velocity outlet's value, so you cannot do the integration process. So then we just assume that the initial height is unknown, so we substitute with h, and then you could get equation for the velocity outlet. Then you compare the flow at inlet and flow at outlet. You do the integration, you substitute the limits, then you will get the answer. Okay, for question number 5 here, so we change a little bit our situation. Let's say we have a wear. Okay, I thought we already learned about the triangular wear and rectangular wear in fluid mechanics 1 when we discussed about the flow rate. So the idea is, okay, let's say to simplify our calculation, so let's say we have a big tank like this. Okay, not so big, it's 2 meter times 1 meter. Okay, and let's say the height is 1.5 meters, but the water level here is actually 1 meter. Okay, and then we have an opening like this, a V notch, or rectangular wear. Okay, so and then you know that water cannot remain still at this area, so the water will flow out. Okay, so we want to know what is the times until the water stop flowing. So in this question, we are not asking you about the time to empty the tank. Why? Because I think you know the tricks. Because the opening of the water is only like this, so mean after the water level reach into this height, okay, the water will not flowing. So means for eternity, okay, the water will not empty the tank. Okay, you cannot empty the tank because the opening, the outlet is only just until 0.77 meters from the datum. Okay, so means that the idea, the tricks of this question is the water is flowing until this level only. That's why in your calculation, you must make sure, you must know how to take the limits, whether you want to take from 1 to 0.55 or you need to put another numbers. Okay, that's our discussion here. Okay, so I hope you could see the tricks for this question. So I will show you how to solve this. Okay, the basic idea is about Q in is equal to the Q out. Then, and usually we expand the equation of Q, of the flow rate, as A and V. So we have A1, V1, and V out, we have A2 and V2. Means that we need to calculate separately. We need to find what is the area, what is the velocity, and so on and so forth. But if you know the value of flow rate for outlet, if you know the value of flow rate, might be you don't know what is the velocity and what is the area. You don't know the area and you don't know the velocity, but you know the equation for the flow rate. So this is okay for you to substitute in the whole equation. Okay, awak boleh nampak equation asal dia adalah Q in sama dengan Q out. Cuma sebelum ni kita pecahkan equation flow rate tu kepada A dan V. Jadi awak kena cari A, awak kena cari V. Tetapi ada kemungkinan, ada situasi di mana awak tidak tahu apakah velocity pada outlet dan awak tidak tahu apakah area pada outlet. Tetapi yang awak tahu adalah equation untuk kadar alih pada outlet. Sekiranya awak tahu equation untuk kadar alih pada outlet, so awak just replacekan di dalam Q outlet. So the idea is, okay, it is not limited for you to know the cross-sectional area and the velocity at inlet and outlet. If you know the equation for the flow rate, so it is okay for you to use that equation to substitute in these terms. Okay, let's say, okay, for V notch or rectangular wear, in Fluid Mechanics 1, we teach you how to calculate the flow rate for the rectangular wear. Okay, the problems of rectangular wear is you have problem because the velocity is not only depend on the height of water. So this is the height of water from certain datum. But the flow rate is also changed because the width of the wear, the width of this triangle wear is become smaller and smaller. So means that the quantity of water that flow out from this outlet is reduced because of the height of water here, the water level here, and the length of the opening. Okay, saya harap awak dapat imagine bahawa dalam bentuk segitiga, bukaan dia ni semakin mengecil. Oleh itu, isi padu air yang keluar di sini nanti juga akan semakin kecil. Okay, maksudnya dia ada dua pemboleh ubah. You have two unknown factor. One is the water level here. Okay, and the second one is the width of the triangular wear. Okay, so now I would like to show you how to derive the flow rate of the triangular wear. So let's say we have a triangular wear, a triangle area like this. And to simplify our calculation, so we have an area here, a very small area. So and then this triangle area, so you have an angle here. So we divide into two, okay, because we want to focus for this triangular area. So now the angle here will become theta over 2. And then we assume that this is an x and this is an y. Okay, so that is our first assumption. And then our second assumption is, okay, let's say we have a small area here. So and then so we assume that the level here to the level here is equal to h, small h, and the total height here is capital H, and we have a width here as b. And because we assume half of this is equal to x, so now we could write b is equal to x. Okay, and then because this is the h, okay, we could assume that the thickness of this strip is delta h dh. Okay, okay, so we start from here. So let's say we have a tangent theta over 2 is x over y, and then we could write x is equal y tangent theta over 2, and y here, so this is the y-axis, so the height of this one, okay, is equal to capital H minus small h. Okay, so I think you could understand this equation because we just replace, we start from this one, we substitute the value of y with h over h, and then we could write b here, mean 2 times x. Okay, so it is equal to times h minus h tangent theta over 2. So, and then we start to calculate what is the flow rate for the very small area. So, this dq here is the flow rate for this area only. Okay, then we could start our calculation by dq equal v times dA. So, v, we assume it is for this small area. So the velocity that comes out from this area is actually constant. So that's why we take a V for that value. And dA here, you know that the flow rate equation is A times V. So A here is the small area for this rectangular strip. So and then we substitute the value here.
Kenapa velocity jadi constant?
Tak, sebab kita anggap kita hanya mengira velocity pada area yang kecil ini sahaja.
Oh, macam tu.
Okey, tak dia gini. Kalau velocity ni dia area keseluruhan, memang kita anggap velocity akan berubah. Sini laju, perlahan sikit, pelan-pelan, akhirnya kosong, betul? Okay, tapi kalau untuk satu area yang kecil ini, memanglah kita kata, kalau kita kata, awak kata memanglah point dekat atas ni dia laju sikit, point dekat bawah ni dia slow sikit kan? Betul. Tapi oleh kerana area ni terlalu kecil, mungkin thickness dia tu 5 cm aja, jadi kita anggap dia almost constant lah. Okey, boleh nampak
Boleh.
Okay, so and then we substitute the value of V. Okay, we calculate the value of V previously. Okay, so and then okay, yang ni saya silap. Alright, so the value of A here, is actually, this is the value of B. Boleh nampak So this is the value of B, and then A is B times DH. Okay, boleh nampak? So this is the thickness. THICK, the thickness. Okay, so we have these strips. So the height of this one is DH, and the length here is B. Okay, now you get this is the value of area. Okay, boleh nampak ke? Okay, and then the V here is the velocity, and the velocity is reflect as square root GH. Okay, so I clear this one again. So you could see that, okay, the A here, okay, yang ini memang kalau kita tulis dalam bentuk dA, dx, dy, kita akan letak dA tu di belakang. Jadi tak proper kalau saya tulis dq sama dengan dA darab V. Okay, so jadi selalunya orang akan tulis dq equal V times dA. Tapi di dalam equation yang di bawah ni, awak kena nampak bahawa ini adalah terms untuk area. Okay. Dan square root GH di sini adalah terms untuk velocity. So, kenapa kita dapat velocity Y? We get velocity as square root to GH because, so let's say we have a weir here. So, this is the water level, let's say from the top here. So, if you compare the Bernoulli equation, so let's say this is 0.1 and then the outlet is here is 0.2. So the pressure is both atmospheric pressure to 0. The velocity at 0.1 here is also 0. So and then we only have the height from 0.1 to 0.2. That's why if you calculate the Bernoulli equation from 0.1 and 0.2, so you will get square root 2GH. Okay, please alert about this. So actually, you need to do the Bernoulli equation for that situation too, but because you already learned it in Fluid Mechanics 1 and Fluid Mechanics 2, so I skip it. So I assume that you know from where square root GH comes from. Okay. So and then we rearrange this equation. So we have this one. Please make sure that you understand that capital H is actually not equal to small h. Because from the figure, we know that h is the maximum height, mean the height of the weir, the height of the water level in the first situation at the initial stage. And the h here is the decrement of the water level. It's totally two different definitions. So, and then now we have Q. I'm sorry. So the equation here is actually about the dq. dq means the flow rate for the small area. Means the flow rate only for that. So we have a V naught here. So the flow rate for this small area. So this is dq. Okay, but we need to calculate what is the value of the flow rate for the whole area. So what we need to do is we need to integrate these terms. So we integrate it. So to get the total Q here, so we integrate. So because we only have dH here, so the integration is only works for the H. Okay, so and then we bring all the constant to square root 2g tangent theta over 2 outside, and then we integrate the value of this term. So we put the limit of h and 0, and then we could get this term, and finally we could simplify. The q here is equal of this term. So this means that this is the flow rate equation for at the outlet. So now, so means that without knowing the area of the outlet and also not exactly know what is the velocity at the outlet, you could still solve the problems, because the main idea to solve this one is you must know what is the flow rate at inlet and what is the flow rate at outlet. So by this calculation, you know the flow rate at the outlet. Then, okay, in this situation, we know that the angle is 45 degree, for example. Okay, so this is a 45 degree. So later on, we divide into 2 to substitute with the ideas of theta over 2 here. So you could find the calculation of tangent 22.5. Okay, you just search you just solve with your calculator. Okay, so but the problem here is to know what is the limit. Okay, what is the limit? Because you will use this limit to in the next calculation. Okay, so the height of the tank is 1.5. The water level is 1 here. Okay, and then the tips here, the end of the triangular weir is 0.77 meter. Okay, you please do not take 1 and 0.77 meter as your limits. So you need to change your limit into 0.23 meters to 0. Okay, why? Because you need to think about the velocity of water. At this point, the velocity of water is 0. Why water not flow out? Because there are no height. You know that velocity is equal square root 2gh. So now the velocity is 0 at this level. Okay, you know, in real situation, the water will not flow out because the water level is reached the bottom opening. Okay, so why the velocity is not there? Because the height is 0. That's why we take this term is actually equal to 0 meter, and then the water level here is actually 2.3 meters. Okay, that's the first reason. The second reason is we reflect the real energy about the water. So if you take this height is 1 meter, okay, you could find the velocity of this
So sorry, I think someone they are accidentally mute the class.
okay, sampai mana Tadi saya cakap dah banyak dah. Hello, hello.
Sorry tak ada, saya putus tadi.
Okay, sampai mana saya terputus?
Velocity.
Sampai slide ini ke slide mana? Slide sebelumnya?
Slide tadi.
Slide tadi Okay. Okay, saya ulang. Saya tak perasan macam mana dia boleh automatic ini dia boleh automatic mute. Okay. So in previous slide, okay, you already know how to calculate the value of flow rate. So means that without knowing the area of the outlet and the velocity at the outlet, you still could solve this problem because you know the equation about flow rate at the outlet. Okay, so maksudnya means that the area and the velocity at outlet is not so necessary. So if you could get the total flow rate for the inlet or the outlet, you still could solve this kind of problems. Okay, in this slide, I would like to discuss about what is your limit to your calculation to find the times later on. So we know that the height of the tank is 1.5 like this, and then the water level is 1 meter. But the tips here, not the end of the V notch or triangular wear is at 0.77 meter. Okay, so the limit is actually 0.23 and 0 meter. Why you need to take this is as your limit, not 1 and 0.77, because you need to reflect the real situation. Okay, we know that if we have an opening like this, so the velocity can be calculated by the idea of square root 2gh. And then in real situation, we found that the velocity at this area is 0. So why this velocity is equal to 0? Because the height here is equal to 0. Okay, and why this velocity comes with certain value? Because it has height which is 0.23 meters. That's why we need to take 0.23 meter as the upper limit, and 0 meter here is the lower limit. Please do not take 1 and 0.77 meters because it will give you incorrect answer. Okay, sampai sini boleh faham trik dia? So saya harap awak dapat imagine limit berdasarkan real situation. Kerana pada ketika air di bawah ini tetap tidak akan mengalir keluar kerana kita kata lubang yang air boleh lalu air tidak sampai pada lubang yang dia boleh keluar. Okay, boleh dapat Okay.
Boleh.
Okay. So then what we do is we comparing the flow in and flow out here. So we have ASVS equal to this equation. Okay, so as I mentioned previously, it's okay for you not to mention what is the area for outlet, for example, and the velocity at the outlet, because it might be difficult for that situation. But you could present the equation for the flow rate at outlet. Memadai kita kata kita lamsam aja. Awak tak perlu tahu apa area outlet, apa velocity outlet, tetapi awak letakkan, awak masukkan sahaja equation untuk kadar alir pada outlet. Then you could fulfill the equation of Q in equal to Q out. Okay, so from the diagram, we know that the area, the surface area here, area at inlet is equal to 2 times 1. and we substitute the velocity at the inlet as dh dt, and this is the equation for the outlet. So you know what to do from here. So we rearrange this equation, and then we could integrate both sides like this, and then we solve the integration works. We put the limit 0.23 and 0, and then you could get that the times here is actually 12.35 seconds.